Structures are imaged by the SDO here, utilizing a 30 nanome wavelength of light, which corresponds to the extreme ultraviolet portion of the electromagnetic spectrum. Timing is important when trying to image these features, as they are more common in certain years than in others. In fact, each structure is dependent on the solar activity of the Sun alternating around an 11-year solar cycle, which I did a video about here. But there's more to learn, just as using visible and ultraviolet light show as different things when looking at the same feature using two different wavelengths of non-visible light can all also be eye-opening to demonstrate this. Take a look at these two images of the Sun's corona taken over the same time period. The following two images use different wavelengths of light, the first imaged at a color temperature of 600,000 Kelvin depicts the quiet corona and features coronal loops. The second imaged at a color temperature of 2 million Kelvin displays the much hotter ACC-IV regions of the corona. The Saint comparison between the two images highlights the importance of using different approaches when investigating the star. What may initially appear to be a singular solar phenomenon can be revealed as a complex, intertwined chain of events. And we still haven't technically made it through the Sun's atmosphere yet, moving further inwards. Let's look at another image produced by the SDO, utilizing a 160 nanome wavelength of light, this time of the transition region. The transition region is a layer which sits between the Sun's corona and the chromosphere, the lowest layer of the Sun's atmosphere. It's a very shallow layer, approximately 100 kilometers in thickness. In this region, the thermal temperature of the Sun rises dramatically from around 8,000 to 500,000 Kelvin. For an earthly comparison, fiercely scalding lava erupting in Hawaii is 1,170 °C or 1,443 Kelvin. The temperature at the lower, deeper end of the transition region is almost 6 times hotter than this. At the upper end of the transition region, the temperature is more than 346 times hotter, traveling even deeper. We find ourselves immersed in the Sun's chromosphere, which is the last layer of atmosphere before we reach the Sun surface, itself imaged here using 170 nanome ultraviolet light. It is estimated to be approximately 1,700 kilometers thick, closely inspecting the chromosphere. We identify some mesmerizing features known as spicules swaying like long, wavy grass blowing in the wind. These long jets of plasma shoot upwards from the Sun's surface as speeds up to 100 kilometers, approximately 282 times faster than the speed of sound, and can reach lengths of nearly 10 kilometers over 1 kilometer, taller than Mount Everest, forming and vanishing in around 5 to 10 minutes on average. The processes behind these spicules were widely unknown and debated for some time, as it wasn't clear how magnetically charged particles could ever escape the Sun's magnetic fields at that level. That is until 2017, when a team of scientists working on an extremely detailed model of the spicules discovered that their origins must be related to neutral particles. Scientists had not originally included neutral particles in their models of the Sun, as they didn't think they affected the motion of the magnetically charged particles. But once they were added, it transpired that the neutral particles gave the magnetically charged particles unexpected buoyancy. They needed to escape the Sun's plasma and shoot up into spicules. Descending further through the Sun's lower atmosphere, we eventually reach the photosphere, the surface of the Sun itself, which is best imaged using visible light, while the edge of the photosphere appears sharp and precise, as it often does to our naked eye. This is simply due to how far away the Sun is. The Sun itself is not solid at all, since it is too hot for matter to exist in a solid liquid or gas state. In any region of the Sun, it can only be plasma, referred to as the fourth state of matter, and is estimated to make up 99.9% of all the matter in the universe. Plasmas tend to behave a lot like gases, except they are made up of a mixture of ionized atoms and free electrons. The photosphere is the outermost layer in this image, around 400 kilometers thick. It is not a fixed solid boundary of the Sun, unlike what this image may suggest. And sadly, it is the deepest layer of the star, which scientists can measure directly. At a closer look, you may notice some dark spots on the left-hand side. These are known as sunspots and appear darker than other parts of the photosphere due to their cooler temperatures. But that's only in comparison to their scorching hot surroundings. Unlike coronal holes, sunspots form in areas where magnetic fields are particularly powerful. Here heat becomes trapped beneath the photosphere. Due to decreased convection within these areas, when comparing this image of the Sun to a previous one, taken using extreme ultraviolet light over the same period, a connection between sunspots and solar flares emerges. The captivating solar flares and sunspots coincide at the same location. From peering beneath the surface, it becomes clear that one must lead to the other. Now let's take a closer look at some similar sunspots. This image was taken using the Swedish Solar Telescope, based here on Earth, and using a wavelength of visible light of approximately 400 nanohm next to and surrounding the sunspots. The photosphere is saturated with these jagged-edged, endlessly shape-shifting cells, which doesn't look dissimilar to lava as it cools and cracks. However, these cells are around 1,000 kilometers wide and are known as solar granules. Consider them from the top layer of a churning convection cell underneath brighter areas inside of each granule. Represent fluid of unimaginable temperatures rising from within the Sun's upper interior layer. To its surface, upon reaching this boundary, the fluid has nowhere to go except to spread outwards and across. After cooling gradually, the fluid sinks back inwards via the rough,